What specific problem does the proposed method investigate regarding vision language models, VLMs, and Bongard problems, BPs?
The proposed method investigates the performance of vision language models, VLMs, in solving Bongard problems, BPs, which are visual puzzles requiring the identification of underlying rules based on a limited set of images. Specifically, the study examines how well different VLMs can discover these rules in both open-ended and multiple-choice settings, comparing their performance to human reasoning abilities. The research aims to identify the strengths and limitations of VLMs in visual reasoning, particularly focusing on their ability to recognize abstract concepts and patterns across the diagrams. Additionally, the study explores the model's perceptual capabilities by assessing their accuracy in detecting specific concepts required to solve selected BPs. Overall, the investigation highlights the challenges VLMs face in visual perception and reasoning, revealing significant gaps compared to human performance.
How does the proposed method or algorithm work? Illustrate step by step, including how VLMs are prompted and evaluated in the context of Bongard problems.
The proposed method for evaluating vision language models, VLMs, on Bongard problems, BPs, involves two main settings, open-ended solving and multiple-choice selection. In the open-ended setting, each BP is presented to the model with a detailed text prompt that describes the structure of the image, including the arrangement of diagrams and the task of identifying two distinct rules, one for each side of the BP. The model is instructed to analyze the diagrams step by step and infer the underlying rules, with the expected response format being a dictionary containing the two identified rules. In the multiple-choice setting, the model is given a similar prompt but is provided with a predefined list of rule pairs to choose from, tasked with selecting the correct pair corresponding to the BP. The responses from both settings are evaluated by an LLM judge, which assesses the accuracy of the model's answers against the ground truth. This structured approach allows for a comprehensive evaluation of the VLM's reasoning capabilities in solving BPs.
Can you come up with a simple yet illustrative example on the inner workings of the proposed algorithm? Walk through the steps using a specific Bongard problem as an example.
To illustrate the inner workings of the proposed algorithm, let's consider Bongard problem number 7, which involves distinguishing between vertical and horizontal elongated figures. The algorithm begins by prompting the vision language model, VLM, with a detailed description of the problem setup, including the arrangement of the 12 diagrams into left and right groups. The model is instructed to analyze the diagrams step by step, identifying the underlying rules that differentiate the two sides. For BP number 7, the expected rules would be that the left side contains vertical shapes, while the right side contains horizontal shapes. The model's response is then evaluated by an LLM judge, which checks if the identified rules accurately reflect the distinctions between the two groups. However, as noted in the results, the VLMs often struggle with this task, frequently misidentifying the rules and being distracted by irrelevant features, demonstrating the challenges they face in visual reasoning.
What are the theoretical or practical benefits of using this method for assessing the performance of VLMs in solving Bongard problems?
The method of assessing VLMs using Bongard problems, BPs, offers both theoretical and practical benefits. Theoretically, BPs serve as a benchmark for evaluating visual reasoning capabilities, as they require models to identify abstract rules across multiple diagrams rather than merely recognizing patterns within single images. This complexity allows researchers to pinpoint specific strengths and limitations in VLM's reasoning abilities, as demonstrated by the comparative analysis of VLM performance against human reasoning. Practically, the structured approach of open-ended and multiple-choice settings enables a comprehensive evaluation of VLMs, revealing insights into their perceptual capabilities and areas for improvement, such as the model's struggles with spatial relations and concept detection. Ultimately, this method not only highlights the current shortcomings of VLMs, but also suggests pathways for enhancing their performance in visual reasoning tasks.
How is the method validated or tested? Discuss the experimental design, datasets used, and the metrics employed to evaluate the performance of the VLMs on Bongard problems.
The method is validated through a comprehensive experimental design that evaluates state-of-the-art vision language models, VLMs, on Bongard problems, BPs. The dataset consists of 100 original BPs, utilizing high-resolution images of the diagrams. The evaluation involves two main settings: an open-ended task where models generate rules for each BP, and a multiple-choice task where they select the correct rule from predefined options. Performance metrics include the number of correctly solved BPs, with results compared against human performance, which serves as a benchmark. The evaluation is further detailed through qualitative analysis of specific BPs, allowing for insights into the model's strengths and limitations in visual reasoning and concept detection.
What results were achieved with this new method, particularly regarding the comparison between VLMs and human performance on Bongard problems, and what insights can be drawn from these results?
The evaluation of state-of-the-art vision language models, VLMs, on Bongard problems, BPs, revealed that human performance significantly outstripped that of the VLMs. Specifically, humans achieved an average accuracy of 41% across the BPs, while the best-performing VLM, Claude, only reached 16%. This stark contrast highlights the limitations of VLMs in visual reasoning, particularly in spatial relations, where they performed poorly, achieving less than 10% accuracy. Additionally, while VLMs like GPT-4o showed some capability in recognizing concepts, they struggled with correctly classifying images and formulating rules, indicating that their perception capabilities are insufficient for solving BPs effectively. These results suggest that while VLMs can benefit from extensive world knowledge, they still fall short in abstract reasoning and visual pattern recognition compared to human intelligence.